test, test. All right, how's the sound out there? I can hear it echo, so that's probably more than enough. Let's see, how do I want to do this? Hello, it looks like we are working. Okay. Oh, amazing. A screen I can use the pointer on. Is this pointer visible at the back? Yes. All right, then I may use it. How do we do that? I know what the last thing that I should do. So for those of you that just got here, I want to emphasize that there is a home game you can play, but it's entirely optional. Everything I'm going to reference when I speak will be on the screen, but it may be compressed a little bit, and you might like to play with it. So that's your choice. You know, I don't. Okay, so we're at the 1 minute mark. So for those of you just coming in, I'll emphasize this is optional. Someone said, oh no, so I wanted to point that out. You can play the home game, you cannot play the home game. You won't miss anything, but for some people it's fun, okay? And I just realized, I said Valgrind, I don't use it in this talk. This repo I've used for some other talks on related subjects, but they're not exactly the same. So I don't actually use Valgrind. And someone commented on the title, SCaLE accepted the second of 2 linked talks, and so the title is slightly less salient, but I like to think it just makes me inscrutable rather than confusing. And I guess that's time. So the title, as you see, is The Young Man in the Sea Reloaded. And what we're going to do is we're going to kind of dive into the deep end of C and C++. And we're going to start with a very simple example. So if you're playing the home game, this is where you find the code. But the only thing we're interested in is this one little function, will overflow. Everything else is kind of driver code, and I'll show it to you. But there are two questions I want you to consider. What is the intended behavior of will overflow, and what will the actual behavior be? Okay? So here's the code. Is that visible back there? Is that readable? Okay. I, at one point, had bolded them to make the green, sort of the letters have a higher contrast, and then the problem was they seemed a little overdone. All right, so the only thing we're really interested in is the behavior of this function called will overflow, and all it does is test whether its parameter in plus 1 is less than in, which of course can't happen in the integers, but of course it does happen in the modular integers. In other words, I'm looking to see exactly what it says. Will this thing try to wrap? Okay? And everything else is just, I try to use it to make a prediction. In this case, I try it on int max, and then we actually do the thing, do the computation. I think I had to move it out of the main, or the optimizer would do stuff. And then it prints, all it's going to do is print the answer. And if you run the little test harness, which actually runs it under several different sets of compile flags, in every case, it does exactly what you thought it would do. Int max plus 1 wraps around to int min. I mean, what else could it do? Okay? And with the optimization shut off, it always predicts that. However, if we turn on a bit of optimization, at 01, it still predicts correctly with GCC. It predicts incorrectly with Clang. Now, if we turn on 02, it fails with both compilers, which means the behavior of that code was both compiler and optimization level dependent, and that's not what we want from a programming language. So the question becomes, why? Now, for comparison, I can take exactly the same code. Notice that the only thing I've changed is the fact that I'm passing in an unsigned. And, of course, I have to test it on uint max and see whether it wraps to 0. But other than that, it's exactly the same code. And what happens, again, it always wraps. But in this case, with either compiler, with any optimization level, the behavior is the same. It correctly predicts it. So the question is, why did it work now? Why did it fail before? All right? So what if I told you the first program actually wasn't C at all? Okay? So at this point, now it's red pill, blue pill time. So just like Neo in the movie, I, like Morpheus, have to give you a choice. You can either take the blue pill, and that means the talk ends, and you can believe whatever you want to believe about C and about your compiler. But if you take the red pill, then the talk goes on, and we explore just how deep this rabbit hole goes. Okay? I won't look if you want to sneak out. Okay, so you're still here. You have apparently chosen to take the red pill. All right? So now the first thing is you might say, well, that first program had to be in C. I just stayed here so I could object. The first program had to be in C because the compiler accepted it. I want you to remember something. The compiler is a machine. The machines lie. Yes? Okay? They don't want you to know you're in their matrix. All right. So what we usually think of is that a programming language has a standard, and the standard defines exactly what the constructs of the language do. Isn't that what a standard is for? That's actually true for some languages, okay, and reasonably close for others. It's probably exactly true for Haskell, because they try especially hard in that community. It's a very similar language called OCaml has, I believe, a hole or two because they care more about performance than the Haskell people. However, C and C++ are actually terrifyingly different than any of those languages, and pretty much any language designed after C, okay, that didn't actually just inherit it from C like C++ did. So there are 4 other possibilities in the C and C++ standards besides actually defining what constructs do. They have 4 different ways to not tell you what they do, okay? In order of increasing chaos and mayhem, you have locale-specific, okay, which is at least opt-in and makes some kind of sense. You have implementation defined, which is not opt-in. However, at least it has to be documented. Okay? There's unspecified, which means they don't even have to document what happens, and I don't believe it has to be consistent. However, and you might think, well, that's as worse as it could possibly get, and that would be true in a sane language, or at least it would be true if the world were nice. But actually, it's not true because there's something worse. For unspecified behavior, the program does have a meaning. You may not know what that meaning is, and you may not be able to figure it out except by running it and hoping it stays consistent from run to run, but it has one. Okay? There is a fourth category in the standard called undefined behavior, and you'll notice it says, upon use of, this international standard imposes no requirements. Okay? Now, if that isn't terrifying, if you're not afraid right now, then you must have misunderstood. So what I'm going to do is I'm going to unpack that at some length so you understand just how much worse that is than at least all of us that have gray hair and learned C a long time ago think. So no means no, and there are ways that people have formulated this. A famous Usenet formulation was, it's legal for the compiler to make demons fly out of your nose. The famous nasal demon formulation. The one I like the best is actually at least repeated by Chris Latner, who's an important compiler writer. Any undefined behavior in C gives license to the implementation to produce code that formats your hard drive. Okay? By the way, every time in this talk I say C, I pretty much mean C and C++, because on this issue there is no difference. All right? So, well, now maybe Chris Latner won't actually go to the trouble of generating code to format your hard drive. Let me tell you what will happen. All right? Although you might read Ken Thompson's paper on trusting trust, because if you're a high enough value target, maybe he will. But the compiler will absolutely do whatever is fastest, and if you invoke undefined behavior, then that will sooner or later create a vulnerability in your code. And there are many volunteers on the net who will be happy to run code on your computer to format your hard drive so he doesn't have to. Okay? And this is not a theoretical thing. Secord works with CERT at Carnegie Mellon, and he points out, you know, the majority of security vulnerabilities in C and C++ programs require or involve exploiting undefined behavior. Okay, and it's not like there's an edge case or two, like in the case, I think, of OCaml, okay, because it lurks everywhere, okay? And I'm not even going to go through this list. I found more than, you know, if my more than 200 here isn't right, I'm not going to count again, thank you. But some of these you knew, but what you don't, you knew you weren't supposed to access beyond the ends of a memory block, but you probably didn't understand the consequences of doing it, and that's what we're unpacking now, all right? So the biggest problem is how in the world did C and C++ end up with a situation where if you invoke undefined behavior, your program actually doesn't have any meaning? And the answer, almost the whole answer, is in this part of the C Standard Committee Charter. Make it fast, all right? And C++ inherits all the same thing. There's some of it is sort of the low-level focus, but performance is really the monster, and it's the consequences of uncompromising performance that we're exploring. So a lot of it, when we program, we usually have some kind of a picture of what we are using. And if we have any picture of a compiler, it's usually this one. So there's a front end which does things like parsing and type checking. And then there's a back end that we hope it does a bit of optimization, sprinkles pixie dust on the code. Okay, what that means is, what we think is that the front end discovers the meaning of the program line by line, just like the way we think about it. And the back end then generates assembly with the same meaning line by line. Okay, so we thoroughly think in terms of lines of C++, or if you're a little more sophisticated, maybe you think in terms of sequence points, but it's all the same. The problem is that this leads us to think that the undefined behavior, sure, it's there for performance. What it's really letting C do is use single machine instructions so that addition does whatever the processor does. It's 2's complement if the processor's 2's complement. Null, you can dereference null with undefined results. because that way we don't have to put in null checks. The problem is that's not the compiler that you have. Now, if you're old enough, it might be the compiler you had a long time ago when we weren't very good at writing compilers, all right? But that was because compilers were stupid then. They're not so stupid now, okay? So this is more like the compiler you actually have. So yes, there's still a front end and a back end, but in the middle, all the optimization is in this middle end. And I have drawn it the way I drew it because this little tiny piece of the compiler in, I don't know, 1970 or whenever, has become the tail that wags the dog. This is most of the code in your compiler. And the reason for that is pretty simple, actually. Determining the meaning of the program is a solved problem and will not grow without bound over the lifetime of the language. Okay? The same is true of code generation, but we have a theorem that says there's no such thing as a fully optimizing compiler. There's always an optimization left to make. So if you are doing your doctoral thesis, in compiler technology, what do you think you're going to do? Yes, that's right. You're probably going to add more code to this, effectively. So the major task of the compiler, still the front end does discover the meaning of the program, essentially line by line. However, then it goes to the middle end. And that middle end is part of an ever heightening arms race between, you know, PhD students and compiler writers, and it's getting smarter and smarter, and it does amazing things to that program and probably erases all knowledge of even what the original source lines were. And then what it produced is handed to the back end. And yes, it does produce assembly code with the same meaning of what it was given, but it gives assembly code with the same meaning as this amazingly transformed program. And the transformed program does not need to have the same meaning as what you wrote. Okay? Now, it does have to have a certain relationship, but the only one is the one imposed by the standard, and I want to go back and point out that no means no. The standard imposes nothing on a program which invokes undefined behavior, really. Okay? So I want to show you how a compiler exploits this because it tends to seem very theoretical. So let's categorize all functions into three types. First of all, there are type 1 functions which don't depend on undefined behavior at all. Those are uninteresting for this talk because the optimizer has to behave and do what you think it should do. So that's not interesting in this talk. Type 3 functions always depend on undefined behavior. So that's also uninteresting because the optimizer, frankly, should just simply remove them. Remove the calls altogether because the fastest way to do nothing in particular is to do nothing at all. So the interesting case is type 2 functions, which may or may not invoke undefined behavior depending on the inputs or some other context such as, acquiring a database handle or something. So the optimizer has a lot of license but not complete license. So what should the optimizer do? What are the requirements? Well, first of all, if the inputs are such that there is no undefined behavior, then it needs to do exactly what the standard precisely defines, okay? And it should be as fast or as small or whatever we're optimizing for as it can be for that case. However, if you pass it inputs that do invoke undefined behavior, first of all, there are no rules. The standard imposes no requirements. And optimization in that case is also meaningless because part of the ethos of C and C++ is trust the programmer, and in particular, trust the programmer to never actually do that. All right? So what that means is that the optimizer should analyze and optimize a function based on the assumption that nothing ever invokes undefined behavior. All right? Because that is the fewest constraints and the most latitude for speeding up the defined case. Okay, so let's take an example type 2 function. This is our friend from a few minutes ago, will overflow. Now that I don't have to squeeze it on there with the driver code, I've formatted it reasonably. Okay, now what should it do with will overflow? Well, first of all, it turns out that the optimizer, so remember, n+1 less than n is our test. Well, the C standard says that adding 1 to in is undefined if in is int max. It does not say that it wraps. Okay? So the optimizer should assume that in is never int max, because that would be not trusting the programmer. So therefore, this test always produces false, because unless it's int max, this is always, the left-hand side is always the larger. So what it should do is produce the same code that it would produce for this function, which simply returns 0. And in fact, that's what it does, because that makefile also preserves the assembly language generated during the compilation. And in fact, you don't even need to read x86. This thing takes a register and XORs it with itself. That's an assembly language idiom for loading 0, which now or at some time in the past was faster and or smaller. But anyway, it's an assembly language idiom. And then it returns. Why? Well, because clearly we can deduce that EAX is the return value register on x86. So what it did, in fact, was return 0 in the fastest possible way. You'll be glad to know that was optimized. All right? So what happened, now you know what happened. All right? Will overflow is a type 2 function, and I passed in an argument that invoked undefined behavior. So that means it has no meaning according to the standard. It's not C, and in particular, its behavior cannot be predicted from the source in that case. The unsigned analog was a type 1 function because the standard actually says that uint max plus 1 is 0. It says it wraps in all cases. So now you might think, well, okay, that was weird, but I've written C, and it didn't seem to always do that. So I want to kind of show you how bad it can be. What if we modify this slightly? I'll do the test differently. I'll check whether in plus 1 is equal to int min. Now, within C, that should always be the same. That should always produce the same results, at least for the way I drove it. Okay, but what actually happens if we test it? Well, once again, it always does actually wrap. However, with GCC on O2, it again fails to predict that it will wrap. Every other case succeeds. Somehow, before, GCC did slightly better than Clang. Now, Clang is actually making the code work all the time, and GCC is not. Okay? What I'm trying to show you is that the results don't, when you get into the area of undefined behavior, the results can not only depend on the compiler and the optimization, it can depend on details of the source that look completely equivalent. Okay? In fact, you can get instability from release to release. I just randomly pulled a bug report out of the GCC Bugzilla. A Bacula developer was unhappy because G++ 6.0 started deleting his checks for whether this is null. Well, so how many of you are C++ programmers and actually got a chill down your spine when I said testing whether this is null? Okay, so yes, that's right. The standard says that that does not happen, and so the optimizer correctly recognized that and removed them. I don't know what he was up to, but it was not the right thing. He also was unhappy about one that seems to be very well known, I hope, at this point. It was deleting calls to memset. Why? Because in the C virtual machine, when you release memory back with free or delete, it's gone. And it doesn't matter that it used to contain your bank account information because it's gone. But of course, in the real world, we like to zero it out. But if you zero it with memset, the compiler knows way too much about memset. And it will look and say, oh, he memset it to 0, then he freed it. The memset had no effect, and so it'll remove it because it's faster. Okay? There's a just as a free tip that's not in the talk, there is in newer Cs, there's a memset underbar S, which the compiler is forbidden to touch. And if you don't have that available to you, write your own, stick it in a compilation unit of its own so it can't do any interprocedural optimization, and trick the compiler into not pulling it out. Okay, so some of the responses on the Bugzilla are quite enlightening. The developer was told, you seem to be confusing it worked okay until now with this code is valid. Or someone more concerned said, it got smarter. And that's what happened. The compiler got smarter, and his incorrect code, which had happened to be working, didn't work anymore because the optimizer was smarter now. Okay? In fact, the standard permits time travel. Doctor Who loves C. Okay? And the reason is that when it says no imposes no requirement, it really means no. So it means that it is permitted, according to the standard, to find undefined behavior, travel back in time and change its mind about doing something sane that it did earlier and do something insane instead. And this actually happens. Okay? And just because that's so bizarre, there's a good reason for that. The reason is, well, it's speed at any cost. But if you want me to elaborate that, the point is that the meaning of the entire program is retroactively undefined, and the reason is it allows more aggressive instruction reordering, which can be a big win on a modern compiler, but it means that if you're hunting a bug which involves undefined behavior, printf, even good old printf may fail you because the error may not be happening at the point, the error may not occur in time where it looks like it should based on its position in the source. All right? So what I want to do at this point, having said that, I want to give you a tiny bit of a different language to say the same thing, because I think it's useful, and it's my talk. When we say a language is safe, I claim we mean something very specific. It doesn't mean, or we should, it doesn't necessarily mean it's easy to use. What it means is every language creates a virtual machine. It creates an abstraction layer for you because the reality underlying it is too hard. And if you think that it's not too hard because you like assembly, I was a physicist once, and I'll keep going down the stack of abstractions until you don't want to do it anymore, which probably will be sometime before quantum field theory. All right, so the point is, what we really mean is that the virtual machine cannot be broken from within. Now, of course, we can break it from without. If you're running a computation and I pull the power cord out of the wall, what happens will not be according to the standard. But that's okay, because of course I can break it from the outside. C and C++ are not safe in a strong and objective sense. Undefined behavior is exactly where the abstraction can be broken from within. And that means that C and C++ as abstractions are leaky abstractions. They're glitches in the matrix, all right? Because you thought you were in the matrix and then you hit a glitch where the simulation didn't work. And the fundamental reason why the source code is no guide to what happens is because source code only has meaning from within inside the matrix, meaning within inside the abstraction. Okay? And that is the terrifying reality of C++. So I wasn't joking when I said the first program was not written in C. According to the standard, it had no meaning. And so the compiler wasn't really obliged to do anything much, so what we got was probably more than we deserved. It actually like printed and terminated and stuff. Okay? So now you swallowed the red pill. You know why, and you know why the compiler accepted it anyway. Because it chewed along with the assumption in good faith that I would never pass it anything that would invoke undefined behavior, and I did. So remember, the compiler is a machine. The machines lie, and they may hurt you if you try to use glitches in their matrix. So this leaves us with the question, well, now what? So we have three options. Well, in the movie, if you recall, Morpheus wasn't really right that there's no turning back because, of course, Cypher got a second chance, didn't he? Or at least it looked like it. So you can go back and take Cypher's choice. You can go back to writing naive C and do what seems to work. You can take the red pill and figure out how to cope with reality, as awful as it is. There is a third option because, of course, the movie wanted to make you make the same choice Neo did, so naturally they would not bring to your attention you had a third choice. You could stand up and walk out of the theater. And we can do that by abandoning C and C++ as individuals, but it's not practical as an industry. There's, first of all, too much legacy code. More importantly, a lot of the ways that we avoid using difficult languages like C and C++ most of the time is by using them to write the critical parts that actually don't work in our more comfortable languages like database servers or native extensions to our languages so that we can get those little bottlenecks done. So the point is, this is not really practical for us as an industry. Also, it's against my principles to give up and let the machine win, but, you know, that's me. And I guess I should point out while we have very few suitable replacements, whenever we do have one, the industry steadfastly refuses to adopt it, so it doesn't matter. Because apparently inertia is the key to technology. The blue pill actually doesn't work either because unless you have very modest goals for security, reliability, maintainability, and so on, it doesn't work because this is where we are. The reputation for C and C++ as being difficult to program in and bug-ridden is really founded on this. It's not manual memory management, which I actually do a talk and teach how to do systematically. There is no system, okay? So we're left with what I'm going to call the red pill approach, which of course is that because I say so. And that is, don't try to know all 200 edge cases in C. Learn to avoid them instead effectively. You build your own abstraction layer by learning what kinds of programming habits will stay away from those dark corners and sharp edges. And what you do is you do them even when you don't need to, until they become habits, because you know what you will do at 3 a.m. on a deadline is whatever your habit is to do, not whatever a smart person would do at that time, because you're not a smart person at 3 a.m. At least I'm not. Okay? And then what you do is there are values, common values between your habits. You internalize those, and then you practice in depth by using tools, which we don't do enough. And finally, occasionally people object, well, but it really, really does work. The answer here is you can't let the perfect be the enemy of the good. It's very hard to do this. Most non-trivial code bases do have undefined behavior in them, at least even high-quality ones. But you can systematically reduce it. And that really is what you do if you choose not to abandon C and C++, or you abandon reliability entirely. Okay? So the problem is that a long list of sharp edges and dark corners I don't think makes for a very good talk. I don't think that's the way to learn it. What I'm going to do is, first of all, I tried to spend quite a bit of time to make it clear to you why this really is an issue, so that you can read things with intelligence and be able to interpret for yourself what the consequences are. And I'm going to do a couple of sort of extended examples as to how I approach this. And then I'm going to give you some references at the end where you can look for more grubby little details on which jagged, rusty edges can cut you. All right? So let's start with the example I've already given you. Okay? And that's will overflow. And what I really want to know is not how I can fix this piece of code. I want to know how I can fix all the code I'm going to write in the future. And I'm going to suggest, to start with, I'm going to suggest that you make it a habit to actually prefer using unsigned variables when you don't specifically need the sign. And the reason is pretty obvious. Why? Because their arithmetic is far better defined. The point is a lot of people will loop on int. Why? Okay, there's absolutely no meaning. What that means is a sign, as a non-negative quantity. The number of elements in the array, or the size of the array, is a non-negative quantity. So, in fact, you're actually violating kind of the implicit contract with somebody else reading your code that you chose your types to mean something like what they really mean. Okay? Sometimes it's actually hard to do. I will say this. I have found that removing unsigned, oftentimes, even if it required some fiddling, has tended to improve the quality of the code. And I uncovered places where I or someone was a bit fuzzy about what they were assuming. Okay? But I'm not saying you do it for that reason. I'm saying you do it because you're trying to make it so that I don't, when I read your code, I don't say, did they do anything undefined with overflow? Oh, no, it's unsigned. I don't have to look for that. I can go on and look for other things. All right? So as a trivial example, of course, this is what quite a few people do and should not be done. It probably has gotten worse because nowadays a lot of people learn to program in a nice, safe, interpreted language that uses big nums for integers. And C uses big nums nowhere unless you go to a lot of work to use a library. The nice thing about this is that size T is not only unsigned, but the standard guarantees it's big enough for any array that you can obtain in C. So actually we should have been doing that anyway, because the meaning we wanted to express was a size, and that's what we should have done. Now, sometimes it's not that simple, and the reason it's not that simple is that oftentimes somebody else or us has used a whole bunch of signed variables everywhere else in the code, and actually, even though it's not undefined, it can sometimes be tricky to deal with the overflow, even for unsigned. Also, if you're dealing with both signed and unsigned quantities, it's actually a pain in the neck to do the conversions and comparisons correctly according to the standard, although they often are just implementation defined, so at least they don't make your whole program meaningless, sometimes, usually. But my point is that a lot of the reason is because someone started doing bad things and then they made more things and more things signed, so the compiler didn't tell them they were doing bad things. And that's what you have to reverse. And so it tends to be infectiousness, so at least get the good infection and try strenuously to use unsigned and let that infect your code instead of signed, unless you actually need negative quantities, okay? And my point is, and I'll keep coming back to this, hard may be hard, but anything is better than leaving hard within the abstraction is always better than breaking the abstraction and being at the whim of the optimizer, okay? And if you don't agree with that, please don't write C for me. Now, there are actually some nice things that, didn't exist a long time ago. So those with the gray hair, probably have habits to not do these. But the C committee is not entirely made up of insane individuals who hate us. It just seems that way. But there are some sizes which actually express things that we often do with things that don't express those sizes, like ints which are large enough to hold any other integer so that you can control the conversions and do things that make sense, or pass them to printf and know that they will work. That's another way to do it. If you need to do something non-portable like hash on addresses, you'll have to be non-portable, but remember, non-portable is better than undefined, okay? It's also, if you don't have one that already means what you want it to mean, you're still probably better off with something explicitly sized than int, so that at least it's consistent from machine to machine, and then please type def it and document what that, int 32 here doesn't mean the same thing as int 32 over here. Thank you very much. Now, one of the reasons you have a lot of signedness is because libc sucks. Now, I'm sorry, occasionally a Unix graybeard gets unhappy with me. I'm sorry, but it's true. libc sucks real badly. And here's an example of it. Read returns a signed size t, an s size t, and the only reason is so it can return -1 so that you know to check error no. Okay? Now, the problem with that is, of course, if you know what size, if you want to compare it with the size of your buffer, and then that leads you to want to keep the size of your buffer with a signed quantity so that the comparison all makes sense, and pretty soon everything is signed, all right? So what you do with this is you wrap it, all right? Aggressively wrap things that don't meet your standards, and libc is a primary candidate for wrapping the whole stupid thing sometimes, or lots of it, because notice what I've done here. Whatever you're using for error values, okay, you return, what I did is I passed in the place to store how many bytes were read, because you'll notice now this can be an unsigned thing that actually means what it really is, a size, and I have separated the results and the error codes, because what people are doing when they return a meaningful non-negative number or -1, or they return a pointer or null, is they're actually faking an algebraic data type, if you know what that is. If you don't, it doesn't matter, but don't fake them, okay? If you don't have them, don't stuff things together and use variables to mean multiple things. This ends up meaning function parameters. You shouldn't have in-out parameters, which is a rule that a lot of people know, but is quite beloved in the C community because it might save 4 bytes on the stack. Remember, okay, so if you really mean at any cost, then I can't help you, okay? So the point is wrap aggressively, all right? And in fact, a piece of advice I got, I love this title, I abuse it all the time, make the compiler your Batman. So I got this from a book written by, I think, an Australian who, it turns out that he got a lot of responses to the first edition, because it turns out that in British Empire speak, this is like British Army lingo for your assistant. But I liked the image, the unintended image of the compiler putting on a cape and cowl and skulking in the dark, striking fear into the hearts of cowardly bugs, that I abused this at every chance. Okay? One of the other responses to that same bug I showed you, same bug report, was someone noted there's an option to disable both of the things that bother you. Okay, actually it turns out that most of us spend a lot of time understanding our languages and apparently no time understanding our compiler. And we should probably not do that because the compiler actually has, when I say the compiler, I'm largely thinking of GCC and Clang. If you use a proprietary compiler, it's still probably true, but you'll have to look, okay? But you can guarantee it with GCC and Clang, and this is a Linux conference, so I don't feel too bad about that. There are a lot of useful flags, okay? And you can do a lot of different things. Some of them will catch compile time errors, okay? In fact, some of them will cost you in some way, but a lot of these are actually free. They don't even disallow things you might have wanted to do. The only reason they're off is fabulous amounts of legacy code, because in 1977, somebody didn't realize that you shouldn't do whatever they were about to do, okay? And so a lot of things are turned off. That's why, how many of you use WALL when you write in C? Okay, I'm a little disturbed it's not everybody, but it's a lot of people. How many of you use W extra? Okay, quite a few people. So those of you that have gotten to WALL have gotten to W extra. How many of you use any other flags besides those that control the interpretation of the source? Okay, I see a few people. Thank you. You guys are in the advanced class. What I really mean is that you can do that, but you can also put in runtime checks, which you may or may not decide you can afford, but let me give you a clue. You can afford them when you're running your test suite, can't you? Okay? Or you can actually change the language into some dialect of C that you find more congenial than the one that ISO envisions, all right? So, you know, maybe the machines aren't entirely evil. Maybe if we ask politely, they might be a little nicer. So, for example, here are some flags that are useful for this particular example I'm talking about. W strict overflow will warn you when the compiler has used the knowledge that something might overflow to optimize. You don't know if it's okay, but at least it warns you that you might want to look and make sure that that's what you meant, because, of course, you can use that even if you're optimizing so much that you're actually using this. It might not be a bad idea to check every once in a while. You can actually have no strict overflow, which essentially tells the optimizer, yeah, don't get so crazy about optimizing that. I don't really know why you'd go halfway, because you can go the whole way. There's an option called FWRAP-V, wrap with a W, which actually fully defines signed arithmetic to be what you probably thought it already was, which is 2's complement, all right? And you can write in that. I'm quite sure that Postgres is written in that dialect, okay? And you know what? It doesn't seem to have slowed down Postgres. You know what? I didn't put in the talk, and I should have. Let me just give you a piece of philosophy. One of the nice things about writing in a fast language is you don't have to squeeze every cycle out of it, because you probably don't need ultimate performance where you might if you did it in a slow language like Python. So you don't have to go the whole way, all right? And in fact, you probably shouldn't unless the profiling says you can't do it. So what about runtime checks? There's a similarly named FTRAP-V, which actually will check at runtime and trap on signed overflow. Okay, there's an fsanitize option. I believe the sanitize family may have come from Clang, but GCC has them now. Fsanitize, signed integer overflow. Now that sounds promisingly named, doesn't it? Okay, so what it does is it prints a diagnostic, which probably you didn't want to do in production, but might be awfully handy in testing, okay? And you can even tell it, hey, try to recover from this and continue. Maybe I could find more errors. I probably wouldn't use that to go to production, but you know what? I'm not your release manager, so. There are also some, I don't have time to talk about conversion, but there are some things that will help you if you take my advice and prefer unsigned. When you do have to do some conversion things, there is a WSign compare to warn you about comparisons that might produce incorrect results. You can at least check them. And if you know they're okay, maybe you can find a way to make the compiler shut up by, say, putting in explicit checks rather than just letting people, you know, figure it out for themselves somewhere down the line. There's also WSign conversion, which does the same thing, okay? It's enormously helpful to have the compiler be your Batman here, whether you think that means assistant or the Dark Knight. I want to point out, when you change the dialect, even if it does not meet your goals or your policy to write to a dialect of C, it's still very handy, because if you are actually writing to ISO C, for most of these flags, your test suite should produce the same results, now shouldn't it? So even if you're not writing to the dialect of C where signed quantities wrap, for sure guaranteed, it shouldn't change the results of your program, okay? You can do the same thing with more than one compiler, because they won't do the same, and they all need to be the same if it meets the standard. So what are some habits that can let us do this all the time? Well, one habit is maybe we should actually get to know our compiler and take it out for coffee instead of, you know, putting in WALL, WExtra, and then hoping we never have to read the man page again. And choose those flags as carefully as you write code, because you know, the compiler knows more about your code in certain ways than you do. More importantly, it doesn't matter whether it's right or not, because it wins. Okay? Remember, non-portable is still defined, and it's still better. There's no upside to being at the mercy of the optimizer. Okay? Now, here's another example. This is an extremely simplified actual Linux kernel bug, so that's why the names are kind of odd. The only thing that matters here is I'm passed in a pointer to a struct, and I'm going to have to do something, okay? And what I'm going to do with this pointer is I'm going to obtain another struct pointer. I'm probably pulling it out of this, but it comes from somewhere. And then what I'm going to do is there's a particular field in this that I want to do something with, all right? However, this could be null, and so I'm going to check that it's null, and if it is, then I'm going to return. I'm guessing that that's what this function might have been doing, but it doesn't matter. I'm going to return, and then the rest of this, I'm going to actually use the value that dev points to. You probably already see the problem. What is the problem? The programmer was probably doing the following. Well, okay, what if I receive null here from dev? Well, this value is undefined if dev is null. On the other hand, I'm not going to use that undefined value, so it does not corrupt my program state. The problem with that is that, I mean, that's the same thing you would use for an uninitialized variable, right? You should initialize them, but if you don't, they don't have to corrupt your program state. The problem is the optimizer is the one that wins, and it says, oh, this is a type 2 function. I can optimize this on the assumption that dev is never null, okay? And then I can delete the null check, okay? So how are you going to fix this? Well, again, you have two possibilities. You can eliminate the behavior, which is undefined according to the standard, or you can define it so it is predictable, okay? If we want to eliminate it, the kernel is written in more or less C89, so I have to have all my declarations first. So I'm obviously going to put the declaration before I compute the value, and of course, I hope we're all adults here and we do know that you at least assign, you don't just leave uninitialized variables laying around as a matter of habit, remember? Okay, then I test it, and now what happens is the optimizer comes to this and says, oh, I haven't done anything with this thing. I don't know whether it's null or not. I better keep the test, all right? Okay, the other way is, of course, if you're in C99 or C++, I personally would do this, but Linus does not like mixing declarations and executable code, so if it's the kernel, you'll do the other, and either is fine. The thing that's not fine is not defining it at all, okay? And the bottom line here is a subtle point, but a profound one. I lied to you when I said what the author was thinking, or guessed. Of course, I said this value is undefined, and the compiler doesn't think the value is undefined. It thinks the code is undefined, and there's a big difference, all right? So how do you make a habit of this? Well, this is actually a habit that I came to at some point, and for more reasons than this, but this is certainly a big one. I make a habit of always laying out my code so that all values get sanitized at the earliest possible moment. And sometimes, you know, your brain tries to kill you or try and tell you that, well, wouldn't it be better if I get my stuff and then I kind of collect all the tests at once? Yeah, it occasionally sounds attractive. I don't do that anymore because I want to couple them visually, all right? So, in fact, the first thing I'm going to do in a function is sanitize parameters. Okay, then the next thing I'm going to do is I'm actually going to acquire resources first. And there are other reasons besides this talk that I do this. I will acquire resources and immediately sanitize and reality check them before I go to the next one. And when I have all my resources, I'll do everything else that might have a non-recoverable error. And then at the very end, okay, now I know I can meet my contract, and I'll do that. But I'll lay out every function that way, even when it doesn't matter, because I'm talking about habits. So it kind of looks like this. I had to smudge everything, of course, but I just used the same. It didn't sanitize the input, but generally you would, okay? So, right, hey, if you passed me null, if I'm not allowing null, all right, I'm just going to bomb out right now, whatever your error handling schema is that you have chosen. Otherwise, I will obtain a resource with that, and then I will check and see if I actually got it. If I didn't, again, I'm going to get out as soon as I can. Otherwise, I'll acquire yet another resource. And I'll check that, and then I'll continue, and everything else, of course, will assume that I have resources, but I will lay it out that way in cases where there's not that much going on and it would be clear. Why? Uniformity, because I'm making a habit so that it'll still work at 3 a.m., okay? In fact, more generally, if you really want to think about the principle that underlies that, what I will do is I will first determine if the caller has met his contract. And if not, I will get out right then and there. I won't try to interpret it anyway. And otherwise, I will do everything, I will first do everything that might cause me to fail to meet my contract. And if I fail to meet it, I will undo anything that needs undoing, and I will get out. And only then will I do the rest of my work, which now I know I'm going to meet my contract. And that, to me, in the long run, if every function is done that way, even when it doesn't seem to matter, I find that in the long run it pays off, okay? So there's another underlying value, right? Do common tasks the same way every time. If I loop through an array from 0 to size -1, and I test, whether the index is less than size, I want you to do that and not loop on whether the index is less than or equal to the last element. Why? It doesn't formally matter, but in C we have an idiom. We track arrays with size, not last index. Please do that so that we all read code rapidly. And that's really the underlying thing here. I'm trying to make something so that I can do it the same every time, everywhere. Okay? And I want to make it look correct. So I always want release code to sit next to I want sanitization code to sit next to the code that obtains it if possible. And in other words, I want logically coupled code to be visually coupled to the degree that I'm able to do that, okay? The other way to solve this, of course, is once again, define the behavior. This may be the best named flag in all of Unix or all of computing. No delete null pointer checks. It just does what it says right on the tin, folks. Okay, what happened here is that this is what the kernel team actually does. And also, by the way, bind does this. And at least for the kernel, I don't think that the issue was they didn't want to fix that piece of code. It was that they expected that they probably had 1,000 other sites where that had been done. And it had always worked. But remember, you can't depend on that to stay forever. And so, as a workaround, they basically now write in a dialect where it's okay to do that. So, one value, and if I kind of have to sum up everything, it's the phrase, don't normalize deviance. And I got that phrase from an analysis of the Challenger accident. And the point was that stuff is falling, insulation is coming off the tank. It's not supposed to. We don't know why. But it never seems to hurt anything. So we'll take the deviant behavior and we'll just sort of define it to be normal. Don't ever do that. Either eliminate the undefined behavior either by getting rid of the code itself and changing it, or by defining it with a compiler flag. Okay? Because again, and this is the thing I keep repeating, what matters most in life, Conan? Well, what matters most in C is not being at the mercy of the optimizer. All right? I'm basically done. I want to point out the only tool I really talked about was the compiler, and the reason is that that's low-hanging fruit. If you don't have a compiler, you're not writing C. If you are writing C, you have a compiler that will help you if only we actually check the docs, and I'm ashamed to tell you how long I used C and never really looked for things like this. But there are many other things you can do. For one thing, there's a whole lot of other flags that you can choose depending on just how much responsibility you're willing to, how much you're willing to keep your code base clean. Different compilers will find errors in different ways, just by the accident of the implementation. And you really would like it to be clean on every compiler you can lay your hands on, all right? Clang actually has a static analyzer project, and most static analyzers cost money because they're boring to write and hard. Clang has a static analyzer project. You already know, I hope, who here does not know what Valgrind is? Immediately go and Google it, because if you write in C, you want to know what Valgrind is. And there are a lot of things like that. It's not part of the talk. Actually, D and Rust are things that would save us trouble, but we can't do that because we're computer people and we don't change our languages. That's it. I want to leave you with a couple of other quotes. Winston Churchill served in the Boer War and said, you know, nothing in life is as exhilarating as being shot at without effect. And that might be how C feels, but you might as well make lemonade out of your lemons and kind of enjoy the kind of control that you get, because you're going to suffer the sharp edges anyway. And that might even be why C is fun. All right, so that's it. I'm done until I'm kicked out, which is probably immediately. Here are what I think are the most useful places to begin reading. It's hard to actually find these things documented the way I said it. But these two are actually blog posts. Both of them are extremely good. There's also an entire book called Secure Coding in C and C++, which comes out of one of the people at CERT, at Carnegie Mellon. And I highly recommend all three of those to begin your journey. What I hope I've done, though, is made it so you understand why the journey is important, and so that you can intelligently interpret sort of the many grubby specifics. And with that, I'm done. I did, by the way, put cards on the back if you want to talk and we don't get a chance to talk at SCaLE, or you want to pay me to do things that hopefully are sane like this. All right, any questions? Yes?
So the compiler will complain that other prototypes don't match functions if you change, say, size.
Yeah.
If I put in a separate statement where I cast a variable from future size tree, my code review is saying you don't have any cast.
Okay, so, well, all right. So first of all, at some point, you know, you have to live within your policy, even if it doesn't make sense. But what I would do is, in almost every case like this, I only want to do it once. And I don't want casts sprinkled everywhere either. So what I will tend to do, I think with more ferocity than most people, is I will wrap things I don't ever want to see again. And I will do it at most once. If I need to, if I have an impedance mismatch, what I really don't want is to fix that mismatch at every place I call it. And so what I will do is I will essentially write a wrapper that has the interface I wish I had, and then I will get it right once. Okay? Now, if your reviewers can't do that, then, well, it would be nice if you would get better reviewers, because I'm sorry, that is the right way to do it. But again, you can't eliminate every use of signed either. There are times when you need it, but there are an awful lot of times when you don't. I don't know if that helped you, but I would wrap them, and I wouldn't put casts everywhere, because you have to read up on the cast. That's very problematic too. Yes? I would say it's not worse, but that is a matter, you know, I'm not your code reviewer. There is a reason why Go, which was designed by very old-fashioned graybeard C hackers, pretty much took all the implicit conversions out because they finally got a chance to walk it back after decades. Yes, implicit conversions are horrible. I have not. I have seen some PL1, and I must say I was sort of amazed, but kind of glad I wasn't using it. But if you think about the age, everything older than C starts to get worse rapidly. C actually taught us many things that we weren't ever going to do again. Other questions? You in the checkered shirt, I think you were up first. My opinions about pointer ownership. Well, as it happens, did I pay you to do that? As it happens, I actually have other talks that I've been known to give, and I have an entire talk or section of a talk where I try to systematically teach memory management in C, largely because I've never seen it done, and I learned it the way most people did by, I'm making fewer seg faults this month than last month, I must be getting better. And when I do that, I explain it entirely in terms of ownership. So my opinion is that if you're not thinking in terms of ownership, you're probably doing it wrong. You're certainly doing it wrong if no one can think about it in terms of ownership. In C, okay? I saw you first. Yes, sir. Well, the answer is it could point at that, but it doesn't point at that at compile time, and the compiler doesn't care, right? So it just does whatever the compiler does, and generally in C, it's actually explicit. Trust the programmer. This must make sense somehow. The point is though that the problem again is not invalid data. That's a problem. In most languages, that would be the scariest thing, is to not understand your program state. What's scarier is to not have a program state, because you have no well-defined program, okay? And so the problem there was far deeper than, this might point at something, something I can't touch, or even, well, in main memory, it's not going to trigger an interrupt because you have an address, a number which happens to be interpretable as an address. But it doesn't matter, because the point is that even well-defined mayhem is still better than undefined mayhem. But the compiler, honestly, must have been okay. I trust him that when it was returned from that other function, it won't have returned null, because if it did, that would be crazy. Yes, sir. Okay.
Why was there so many returns? The second part is lambdas. How do you feel about lambdas? And third is the same, almost hitting on the same point, but the known new as far as 14 is concerned go around.
Okay, so the first part. Let me hit the first one. So the first one was. Yeah, I will repeat it. I wanted to listen. So tell me again. I wanted to hear all of them. The multiple returns. Okay, so the question was, I did a whole bunch of things like multiple returns, which your programming teacher in college, I'm exaggerating for effect, but my programming teacher didn't like them. Okay, this comes, okay, so, right, well, you have invoked my undefined behavior, because now I get to rant for a second. What you have touched upon is a glitch in the matrix where what teachers of programming say does not actually fit the needs of the industry. This is my opinion, and since it's the end of the talk, I can be a little edgy. The fact is that, yes, there was a time when people energetically pushed the idea that every block of code should have a single entrance and exit, and since a function is a block of code, it should have one exit. That's the origin. Now, let me tell you what happened. And Dijkstra, Edgar Dijkstra is the most famous exponent of this. Let me tell you what happened. Actually, let me ask you a question. Do you know anything about chess? Okay, so do you know how you implement chess on a computer? Okay, well, so the answer is you do it very differently than a human being does it, okay? Because a human being is actually not very good at looking very far ahead on dozens and dozens and dozens of lines. But we're really, really good. Well, not me personally, but a master chess player is very good at recognizing lines which don't make any sense by essentially pattern recognition. So we are not very good at following trees, but we're really good at pruning them. Computers are essentially the opposite, okay? Computers are really good at following many, many. So the point is that for a computer chess player, you will get a lot more of your ability to play from things like look ahead than a human will, and less from your position evaluation. Why do I say that? Let me tell you the dirty little secret about that. The people who benefited the most from the idea that blocks of code should only have a single entrance and an exit were people who wanted to prove theorems about code and people who were writing compilers. And what they're really saying is do a piece of what the compiler does, because if you look up basic blocks on the internet, you'll find that that's pretty much what the compiler does internally. The real question for me is, as engineers, does this help us? And the answer is it does not. Because we are good at pattern recognition, and okay, so the bottom line is that you have two choices. You can have one exit and have code nested more deeply, and sometimes guard the whole thing with these big ifs, or you can bomb out early. And the problem is that the way we actually understand code, I claim, certainly what I do is I read down and I like to know, okay, you know what? I can quit thinking about null because I've just checked for it. So as far as I'm concerned, multiple returns are not only fine, but there are 3 cases where I will accept goto. Now, only 3, unless you can convince me that I missed one. But the fact is that when you do exception handling in C, the idiom actually is probably to use goto. But that's not what this talk is about. The bottom line is that I do that because I actually think it's clearer. And, you know, at this point, I don't usually rant about that because that argument is so 70s. Except you still get people who come right out of school and they don't want to do those things. And so that was, I don't know if that was the answer you were looking for, but it certainly is. I'm perfectly willing to do that. Okay. So the second question, actually I should probably,
make it even better.
Okay.
Define versus, creating macros versus,
Oh.
Going with
Okay. Oh, macros versus, well, templates are really only C++.
Yeah.
So if you're in C++, of course, you can find a way to not use a C macro for almost everything, and you should. So, I mean, that's almost uninteresting because even if templates are confusing, they still make some kind of sense within the type system. So, yeah, I mean, I would use a template pretty much anywhere if I could avoid a macro. You could probably find a case where that's not true. But in C, it becomes harder because you don't have the templates available. Anybody else? Yes, sir.
You mentioned writing unit tests.
Yeah.
What tools or library do you use to make it easier to write tests?
You know, it varies somewhat on the project. I can't remember the name right now. There's a very nice unit tester for C. Let me tell you instead what you should look for in a unit tester, all right? As long as you're doing the test on, a real computer, the way a C unit tester should work is it should fork off before it runs every test, because in an unsafe language, there's simply no other way to keep bugs from possibly screwing up whatever your tester is, okay? And there's one that I just can't remember the name. But the funny thing is that if you're writing for an embedded system and you want to run your test on the embedded system, you probably don't have fork available. But you know what? There is okay, so I'm forgetting all the names. There is another unit tester which is almost the ununit tester. It's like 5 lines, it's like a header file with like 5 lines of C that you include, which actually lets you do it quite easily. So it turns out to be really easy to do, and although I'm kind of unhappy that my brain has quit working, it's actually very easy to find on Google. But what you're looking for is either one which is smart enough and has enough machinery to fork off the test so that you have the process boundary between the code which might be writing crazy stuff to crazy places and the code which is supposed to notice that it did it, or you probably want to make it really simple so you can run it on anything that can run C. Okay? I really should have those names on the top of my head. I'm sorry. Anybody else? So, looks like maybe we're done. Thank you so much for coming. I have cards at the back if you want for some reason. Yeah.
Occasionally, I'll do C or C++ programming, but most
Yeah.
of the time I'm in higher level courses.
Yep.
I've
Okay, welcome everyone. Imagine that you're the owner of this website. You spend your weekends doing research for new recipes, engaging with people that come to your blog, posting comments all day, and you really care about it. It's your baby. It's everything you do outside work. However, there is something that worries you a lot. Every now and then, you get emails from people saying that you are selling their information to corporations, that every time that they go to your website, they see advertisement and they don't know where it comes from. And this is very puzzling for you because you know that you don't have any advertisement in your website. And you know that you are not selling any information to anyone. So you start doing some research and bump into this blog post from Google Security that says, if you don't enable HTTPS, we're going to tell everyone that your website is insecure. And you start wondering, what the hell is HTTPS? And then you also see comments on Twitter like this, where you discover that ISPs inject information for their users to pay their bills. Or like, if you download torrents, your ISP will inject banners in websites telling you to stop doing that. And it gets worse because they might also inject advertisement, completely unrelated to your website. You might be the Stanford University, but a random ISP might inject jewelry advertisements in your website. What the fuck? So at this point, you're completely sure that you want that HTTPS for your website. You don't want this to happen to all the nice users that go to check your recipes. You don't want people to see this in your website. So you do more research, and you land in this page. I want you to sync the message in. You want your customers to come back? Give us money. That's basically what it says. It sounds like a ransom to me. So you're like, I'm not going to pay just a company for something that I don't even understand. So you keep doing some more research. And you arrive to this other page where it says, CDN, continuous development, and one-click HTTPS. And someone told you that this place gives you the HTTPS for free. So it's like, oh, this is pretty nice. So I can have it for free, and it says that it's just one click. And besides that, Netlify has a built-in CDN, so my website is going to be faster. That sounds pretty cool. So you sign up, and when you try to configure HTTPS, you arrive to this page where it says, free on all Netlify plans. Just click on that button at the bottom, and that's it. And this, for many people, sounds like magic. It's like, I don't understand what it is, but I just clicked the button and it worked. So that's pretty cool. And today I'm here to actually tell you that it's not magic. I'm here to tell you how it works. So at Netlify, we use this certificate authority called Let's Encrypt. And Let's Encrypt it was donated to the Linux Foundation. So it's free, it's automated, and it's open. So it's free where you can get a certificate for your website or for anything you want for free. It's automated in a way that it's basically an API. It doesn't even have a user interface. Like, you cannot go to let's encrypt and like download traditional certificated text file or anything. It's just an API, and it's open. So you can contribute, you can see the code, you can help them. And for many people, this is a game changer. The fact that it's free, it's like anyone can get certificate for free. And it's actually a game changer. It's automated, besides being free. We have seen in the last year how platforms took advantage of this. Like, people don't need to buy certificates anymore. And people don't really need to know what a certificate is. Because at the end of the day, they only want their websites to be secure. So platforms like WordPress.com just made all their websites secure for everyone that hosted with them. And they didn't have to ask people to go to a third party, pay them for a bunch of files that they don't understand, and so on. They just integrated with Let's Encrypt and made all their websites secure by default. And we saw that again with the Squarespace. They did exactly the same. They wanted to make all their websites secure, so they just did it. Their users didn't have to care how the connections between Squarespace and the people that go to visit their websites are kept secure. They just need to know that it's secure, right? And Etsy wrote a blog post in the same way too. This is how we made all the websites for our customers secure for free, without even like asking them like about anything. We just did it. And this is really the game changer. At Netlify, we don't do this by default yet. It's our goal to make it by default this year. But so far, just by having a one-click button, we have seen that like more than 60% of the people that put websites with custom domains with us, like just have secure connections. And again, the goal this year is just to make everything secure, because there is no really point to actually keep serving websites in an unsecure way. Let's Encrypt is based in a draft standard called ACME, Automated Certificate Management Environment. It's still a draft, so it changes every day. It's also open source. It's the draft itself. It's been discussed on GitHub, so you can go there and see the draft. You can contribute to the draft. You can fix everything you want to fix. There are a lot of typos in the draft. There are a lot of fixes for typos. So I'm going to explain you how ACME works. In essence, ACME is basically like a traditional certificate authority, but again, it's API-driven. There is also an open source implementation of ACME called Boulder. It was also donated by Let's Encrypt. So if you want to see how the standard is being developed, you can also see it, and you can also contribute to it. There are people from the Linux Foundation contributing, there are people from the EFF contributing to it. There are a lot of people involved in it. We're going to talk a little bit about the way that ACME transport messages. The main characteristic is that every message, every request sent to the ACME authority is signed with a JSON web signature. And that basically means that every request sends its content in a JSON payload, which includes a protected header with information that we'll see later, an unprotected header with information that to interchase in an unsecure way, then the payload that you want to actually send, and also a signature to verify, so that the server can verify that actually the request is the original request and it wasn't tampered with. It has replay protection, so the server, for every request, generates a nonce. And it keeps in memory all the nonces that it sends to the client. So that way it can guarantee that an attacker kind of like try to replay previous requests. And all this is inside the draft. So this is, by default, ACME is very focused on making this secure too. It has request URI integrity. So inside the protected headers, the client also sends the URI where it's supposed to send the request, so the server can verify if there are not people in the middle tampering with those requests. If the URL inside the protected header matches the URI in the request, then that's a valid request. Otherwise, the server just denies that request. And we're going to see a little bit about how the certificate management works. The first thing that you need to do to start issuing certificates basically is to sign up. So you need to create an account, and you just need to send a request to the API saying that you agree with the terms of service, and just give a contact email, like any traditional authority. And when you do that, you're done. You have an account with them, and you can start issuing certificates. When you want to issue your first certificate, you basically send a request saying, I want a certificate for this domain. The domain is, it's a type DNS. We'll see what that means later. But you basically give the domain name, and the authority validates that, and now we'll see how it actually verifies that and how we issue the certificate. This is what's called just the authorization, and the response normally is pending the first time you send the request. The authority has a bunch of queues where it processes millions of certificates, basically. So it's not a synchronous process. The first time that you send an authorization, the request goes to the queue and it starts impending, right? It also gives you these 3 challenges. A challenge basically means, okay, you give me a domain. Now I challenge you to prove that you actually control that domain. And there are 3 types of challenges: HTTP1, TLS2, and DNS1. The HTTP1 challenge means that in order to prove that you control that domain, you have to provision a file in a path. So the authority will send a request to that path. If what's in that path matches the SHA of the key authorization that you send it, then they assume that you control the domain. The DNS challenge is very similar, but it uses a DNS record. So if you want to prove that you control the domain, you just create a TXT record under that subdomain. And again, if what's in that record matches the SHA of the key authentication, then that's valid. So you're good. And then TLS2, which is, again, very similar, but it uses TLS negotiation. So the authority will try to request a certificate from you using just a simple client hello. And if the certificate that it receives includes the key authorization, then you're good. If you're wondering why HTTP1, DNS1, and TLS2, it's because the standard is designed to actually evolve those challenges. And the first version of TLS, it was TLS1, obviously, but it was proven that it was faulty, so they improved it, and they they just changed the version to TLS2. And the version that's in the standard now, it's TLS2. However, Let's Encrypt still doesn't support the TLS2 standard. It's still a work in progress. It's going to be released as soon as the draft is slightly more stable. Once you have proven that you have access to the domain and that you control it, you can send them a certificate request. And basically what you get back is a bunch of links to get certificate information and also the final certificate. And when you have the first certificate, you can just do whatever you want with it. You just put it in your website or use it in the way that you want to use it. Obviously, you don't have to do this manually or like write all the code yourself. There are already a lot of libraries to do this. The most well-known is Servbot. It's basically a command line application. It was donated by the EFF, and you just run Servbot on your machine, and it does all the negotiation for you. It verifies the challenges, and it downloads the certificate. Besides that, it also schedules, I think, depending on your system, it uses cron to actually schedule the renewal of the certificate, and so on. So you don't actually have to do anything. There are a lot of other options. I think at this point, there are libraries in every known programming language. If there is none, it's probably because the language is not very well known. But otherwise, I think there are like libraries in every single language at this point. So I'm going to talk a little bit about how we provision certificates. There are 3 main points. Basically, the first thing to explain is how we provision certificates for users when they go to visit a website. So basically, when the browser sends the client hello request to our servers, it reaches the CDN network. We use Apache Traffic Server as a proxy cache, and it has a specialized plugin that when it gets the client hello request from any user, it goes to the origin servers, and if we have the certificate, we just give it back to the edge nodes, and the edge nodes do all the negotiation with the client, and that's it. And then we serve the website. If we get another request from other user to the same node, the node will directly return the certificate, and everything is good, right? This is the happy path interaction. There are unhappy paths that we'll talk about a little bit later. Then the second part of this is when a user goes and says, yes, I want a certificate for my website, and click that button. And this works in the way that I explained before, where like our API, when we get the request, the API will enqueue a job, and then we'll contact the authority, we'll issue an authorization for the domain, we'll generate the challenge, and then we'll wait until the authorization is completed, and if it's completed, then we download the certificate and we store encrypted and secure for the next time someone tries to reach the website, and then we go and serve it. And the way that we validate challenges currently is using HTTP1, because at the end of the day, it's as secure as TLS01, so it doesn't really matter that much. And since we control the origin servers, we can just serve that path with the authorization content, and it's a fairly easy integration. So now I'm going to talk a little bit about what we've learned, and also the unhappy paths. Nobody knows how DNS works. And this is also like kind of recurrent on this talk, because if like a person just wants to like put content online, why do they need to know how DNS works? Like they just want to put their content online. Like why do they need to know like how servers communicate to each other? The problem is that if you want to host your website and you have your name, and you give all the content to someone else, you actually have to point your name to the servers. So you need to know how DNS works. Let's Encrypt obviously uses DNS to resolve like where the domain lives. And if the DNS is not completely propagated, they won't find the right server. At the moment, we actually do a very bad job at telling people that their DNS is not propagated correctly. Because if you notice that the screen I posted at the beginning with the button to provision the certificate is just a button. So you can click it at any moment, right? So you can just change your domain and click it. And obviously, the DNS is not propagated at that point. So we're going to try to provision a certificate for a domain which DNS points to somewhere else. And then like nothing is going to work, right? We're going to get SCaLE certificates. We're not going to get a certificate. And all those kind of weird corner cases. The second problem is that Let's Encrypt has actually, there are fair rate limits to avoid abuse. And basically, they allow you to request 20 certificates per week. And each certificate can include 100 names. So there is a lot to request. You can, like, in a certificate, you can add a lot of names. The problem is that Netlify integrates with Git in a way where if you have a repository and you, let's say example.com, and it lives in your Git repository, if you create a branch called staging, we're gonna provision the contents of that branch on our servers, and we're gonna allow staging.example.org to serve the contents of that branch. And if you have a certificate issue with us, we'll provision the certificate for your new branch. And this sounds pretty cool, but if you work a lot with branches, we'll end up trying to issue a lot of certificates, which can reach the limit pretty fast. And then, besides that, Let's Encrypt keeps track of the certificates that you request per week. So, for instance, if I create my branch staging, I request the certificate for staging, and then I remove the branch. I'll request another certificate for the previous state of the certificate without the branch name, and that will incur into a duplicate certificate because I already asked for the same certificate with the name. And again, that limit becomes actually not that fair when we request a lot of certificates. No, I don't know what happened there. All right. And third, obviously the network is never reliable. We're dealing with a distributed system, so we can send requests to Let's Encrypt, and they might never come back. Or we might try to send a request, and the request never arrives there. So we're not doing the best work at actually keeping track of those kind of things. And now how we're going to make all this better. Obviously, you might already think ways to solve all these problems. The first one is that we're going to expose DNS information to our users, where before they can click that button, we're going to tell them, well, the DNS is not propagated, so that's not very useful for you to click right now. We'll let you know when like the DNS is correct, and you can actually issue the certificate. We're going to try to like batch the request that we send to Let's Encrypt, and we're actually already keeping track of the limits to make sure that we don't incur to those limits and we don't get penalized. We've already implemented part of this, but we have a better delivery guarantees. Let's Encrypt gives you a unique URL per resource that you ask for. So if you try to create an authorization, that'll give you a unique URL. We keep track of those kind of things so we can replay those requests without actually trying to gain the system. And finally, we're going to make it open source. The new system that we're designing is completely independent from Netlify. So if other company wants to start issuing certificates with Let's Encrypt, like WordPress or Squarespace or Etsy, they wouldn't have to actually implement the whole system again. All in all, HCPS has reached a limit where like there is no going back, and the sooner we can make the web 100% secure, the better for everyone. Mozilla has seen on their servers that more than 50% of the traffic goes through secure connections already. This graph is actually flawed because it includes pages like Facebook, Gmail, Google, Twitter. This doesn't mean that more than 50% of the web is already encrypted. It only means that the pages that people visit the most are encrypted. And that's it. Thank you for listening. We have time for questions. All right. Yep.
How have you tackled the browser support? And Encrypt has been kind of...
Yeah. The question is how we tackle browser support. At the moment, the major browsers already support their certificates, so there is no issues there. Only like all browsers have issues, and we actually cannot do anything there, really. The traffic that we see comes mostly from like up-to-date browsers, so there is nothing that we can really do right there.
When someone pushes a button, if someone hits it with their own browser, does it fall back?
It needs to be a very old browser, and I don't think we have ever seen like any issue like from people saying that the certificate that we try to serve is invalid or like. Yeah.
So what happens when you hit PBS?
They just reject your requests. Just like, and there are also like, depending on the limit that you hit, that domain can be like banned for a week. So we also talk with them a lot. Yeah.
I remember years ago the duration of the certificate was very short, so you had to keep authorized cancel, and therefore your website was kind of a hostage of Let's Encrypt. That's still true, what is it like?
So the question is, what's the life of the certificate? That's still true. Like, it only lasts for 3 months, so you have to constantly keep renewing it. It's actually more secure because we revoke a lot of certificates, and we see like people that stop like browsing their website, stop like updating their websites, or even like removing their websites, and we just like kill the certificate as soon as like they do this. But at the end, it's for us it really doesn't matter, because it's just like we have a scheduled task that every day like takes the certificates that are going to expire in less than 30 days and it tries to renew them. For users, it really doesn't matter because they don't have to do anything. Again, I mean, we have never had any issue with renewals or anything like that. It's just you have to do it every 2 months instead of like every 2 years or whatever. Yep. Do I have any experience with Cerbot and the ways it works? As a user, I've used it. I don't know the internals to actually tell you like if it really works or not. I know like it works like for Apache or Nginx. It really works. It's very easy to because their configurations are fairly standard. I know, for instance, it doesn't support Apache traffic server. So if I try to, like, the way that Cerbot works is like, if you have an Nginx on your server, it will configure Nginx to serve the challenges. And obviously, like, it does a lot of things to make sure that Let's Encrypt can actually reach your server, right? Yeah. Yeah. The configuration is like, for things like Apache or Nginx is fairly standard, and so nothing really complicated. And it's also open source, so you can just go there and see it. Yeah. Yep. The question is, do I have to do the 3 challenge or just one? You have to do the one that you pick. The authority sends you the challenges, and you pick one. And then you tell them, the ones that you pick, you tell them, use HTTPS, and that's what they use. Yeah. Yeah. The question is there a single CA on the backend? No. Let's Encrypt certificates are also signed by a third party. So it's not just their certificates. Their certificates are signed by someone else. Yeah. The question is there a path for certificates without a public network, right? There are ways to do it. There are different ways to do it. For instance, Docker Swarm issues certificates with Let's Encrypt for their clusters, and they can be like private clusters. It depends also like on your configuration, but yes, there are paths to do it. Yeah. The question is Acme capable of handling those pathways? So it really depends on your setup. Like you actually, at the end of the day, you have to expose something publicly so Acme can actually reach and validate the challenge. But it doesn't have to, you don't actually have to expose your whole network and things like that. Normally for those kind of things, I think DNS might work better because you don't actually have to expose servers. You have to just configure a DNS entry in your DNS record, and then you remove it. Like you don't have to. Another thing is that you don't have to leave the challenge there forever. You just like if you try to validate the DNS, you can just put the record there, and as soon as the authority validates the record, you just remove it. Actually, leaving it there, it would probably be a security issue for you. And all the clients already handle that. Like, if a client uses DNS challenge, the way that they do is like, you probably give them an API key for your DNS provider, and they will create the record, and as soon as the challenge is validated, they will remove the record. Yeah? Is there any other authority that uses Acme besides Let's Encrypt? Not as far as I know. Yes. Yes, you can. Yes. That actually, Boulder is very easy to run. Like, they did a very good job at, like, well, if you want to run it, if you don't want to run it in a production system serving millions of certificates, it's very easy to run. All right, okay, thank you very much.
Test, test. Can y'all hear me okay? Is that good? All right. Test, test. All right, welcome. Can everybody hear me okay? Too loud? Too soft? Good? All right. Welcome to Debugging Hun Python Processes with GDB. My name is Brian Bouters, and before we get into the talk, I just want to take a photo from up here. If I can just get everybody to smile and look like you're enjoying yourselves. Great. So thanks for coming, and thanks to all the organizers and volunteers who've helped to put SCaLE together. This is a great event. It's actually my first time out here, and I've really been impressed with the diversity and the different tracks that we've had here. So big thanks to everybody who puts this together. So debugging Python processes with GDB. This is something I had to learn out of necessity. I did not seek out this topic. It found me because one day I needed it. And I hope you never need this. But if you do, you can use these tools and techniques to get some insight into what your Python code is doing. There's a couple different situations that you would want to do this in, and we'll go through those. But the thing I want to highlight here is that I'm no expert. I'm a Python developer. I've been working with Python for a long time, but I kind of just had to learn these techniques. And so don't be afraid to try them and to experiment with them and play with them. We're going to have some really simple examples today. This QR code here does link you to the slides. They will also be available on the page for this talk later today or tomorrow. And the same QR code is here at the end so that you can find the content later. So with that, let's go ahead and dive in. A little bit about me before we move right into the content. So I'm Brian Bouters. I've been a Python user since about 2005. It's my language that I work in. It's the language that I play in. I really love using Python. And even more than Python, though, I love free and open source software. And I think that's just something that's shared by so many people here. So I won't tell you too much about my love for it because I feel like you probably share that. I'm a principal software engineer with Red Hat since 2015, and since I've been with Red Hat, I've been working on this project called Pulp, as you can see on my shirt here, which is a software repository management project, and you can learn more about that at pulpproject.org. I won't tell you too much more about that, but I'll encourage you to go check the project out, and if you have any questions about it, I'm happy to answer that for you. I contribute to several open source projects, Kombu and Celery. Those are kind of messaging libraries and applications in the Python community. So if you have asynchronous work or long-running jobs that you want to get done in a scalable and organized way, Celery, for instance, is a great option to look at. It's very popular, so probably many of you have already heard about it. So I'm a contributor to both of those projects, and a core contributor to Kombu. So enough about me. Why would you ever want to debug Python software with GDB? I mean, seriously. Debugging's hard enough. GDB probably doesn't make it any easier, I mean, when you think about it. And I come from, I've had some C experience, but I grew up kind of with interpreted languages and really got interested in programming when they had already kind of taken hold. And so I don't come from a C background. I come from a Python background. And so that's maybe why I don't feel like an expert deeply in this area. But there are some very good reasons why you might want to debug Python software with GDB. It's things like this. So who here has, let me do a couple of show of hands here, a couple questions. So first, who has ever used GDB to debug Python before? Raise your hand. Oh, wonderful. All right, great. And I'm sorry. So who here has ever experienced an issue where somebody calls you up or messages you on IRC or sends you an email and says, look, I got this problem. I'm experiencing it right now. It's in the production environment. Can you please help me? And then you say, yes, I will try. I'm going to try to reproduce it back in my developer environment, and you cannot reproduce it. And you try hard, and you ask your friends, and you ask others, and you get more information, and you still can't do it. Because there are just some situations where you cannot effectively reproduce a bug back in your developer environment. So what are some reasons for this? It's a very rarely occurring issue. In my case, the bug that I was chasing for quite a long time was occurring very, very rarely, so maybe only once a month on systems that use Pulp in high volume. Secondly, it wasn't actually in our code, as it turns out. It was in one of the libraries that we were using. And so, the deep knowledge about how our application is written and works was not helpful to us. And also, the symptom was terrible. It was rarely occurring, but it stopped your pulp system pretty much cold. It was a deadlocking issue that when you experienced it, your system would be in this state where you had it. Like, it occurred. No more tasks would process, and the only thing you really could do was restart some of your processes, and that would just, everything's fine again. So some people, they see something weird, and they just restart the processes and just keep going. But as a developer, I need to make sure that this is working great all the time. So in cases where you have a defect and it's something that occurs rarely or remotely, for instance, that's situations where you would want to use this. And talking about the remote aspect of things for a moment, perhaps, there are things like RPDB for remote debugging, right? But perhaps you can't connect to this other system where the environment is running, where the application is running, because you just can't reach it because it's firewalled off or it's behind some networks that you can't get into for whatever reason. And so remote debugging on that live system is also not an option. And so, these are some of the reasons why you might want to use GDB to debug this, because GDB is a great tool for getting insight into what is going on in this Python application in this production environment. So, yes. So you can use it where PDB can't go. You can use it in remote applications where RPDB cannot go. For rarely occurring issues, that was the case that I was experiencing. Well, also, I couldn't connect to these other places, so RPDB was not an option. And also deadlocking issues. So places where you're just not sure if it's doing anything. Like, is this code even doing anything? I mean, you run the Python, you run the application in Python, and it's hard to know. It's hard to get insight into what is going on inside this application right now. And so that's the kind of problem domain that this technique is very useful in. And like I said, I hope you never need it, right? Because you should always be trying to use PDB and RPDB first. So simple poll here. Who is debugging with PDB, for instance? I expected to see a huge amount of hands up. If you're not using PDB, you should be, or some other interactive debugger. If you're writing print statements and things like that and running your application, really consider switching, because PDB is just an excellent tool. So that's tool choice number one, all right? Use PDB. Say it with me now. No. So who's using RPDB, which is a remote version of PDB? Okay, so that's really great if it's just like PDB, but you can connect to a remote system. And the way RPDB works is, actually, I'm going to show you real briefly. This is a talk on GDB, but I just want to show these real simple. So yeah, PDB, this is what you should be using. It's part of the standard library. It's the Python debugger, so please use it. RPDB is a package you can find on PyPy. And what you end up doing with RPDB is you put this line in your code. And when this line is experienced, it halts your program. And it opens up a network listener by default on port 444. And then what you use is something like Telnet to connect to that port. And you can interactively debug the whole stack. You can go up Python frames and down Python frames and check out the local state and look at the stack and look at the variables that are deployed. And so this is really great, but again, if you have a rarely occurring issue and it's in production, maybe you can't reach it, you can't do this. And secondly, you have to put the lines of code in there, right? And so when you stop the application, insert the lines of code, which you probably can't do on the production system anyway, but even if you could, when you start it back up again, if it's a rarely occurring issue like mine, it does you no good. Oh, look, it runs great. And, so this is just a non-starter for debugging those kinds of rarely occurring issues. But use these tools. These are the preferred tools. Do not do the GDB stuff. I mean, you can for fun. I think it's fun. But so the conceptual model here is that what we're going to do is we're going to use GDB, which is, I should have said this from the start, it's the GNU debugger, and we're going to use it to debug CPython. So a little bit about these boxes. So the GNU debugger is the debugger for debugging compiled languages of a variety of types. Most people just think of it as the thing you use to debug C with, and that is probably its most common use case. But you can use it to debug a variety of compiled languages. And so as it turns out, but CPython, which is the Python interpreter, is written in C. And there are other interpreters out there. PyPy is a different one. It's also written in C, but it's just a different implementation that can read the Python code and provide the guarantees that the Python spec requires to make the language work correctly. So there are different interpreters, if you haven't thought much about that. There are others too. But CPython is the reference implementation, and it's the one that if you're just running Python on a system and you're not really thinking about what interpreter you're using CPython. So the idea here is that we're going to use the GNU debugger, GDB, to connect to CPython, the interpreter, and we're going to, in a way, do what a CPython developer would do, right? We're going to use a C-based tool to inspect the state of the interpreter itself. And through this, we can learn all sorts of interesting information, useful information about what your application is doing. And you can see the box here. I'll just describe it here so everyone can understand. Above the CPython box is a Python code box, which is your application itself. And so your application code is having its code fed into and interpreted by CPython itself. So that's the conceptual model. Any questions here before we move on? All right. Okay, so this is a very simple example. This is example.py. And just to describe it a little bit, it imports OS and time, and it defines two functions. One is foo, which displays the PID that the process is running as. And then foo calls bar, and all bar does is sleep for 30 seconds to give me enough time to connect to it and show you the awesome. So at the module level, foo is calling, the function foo is called. So just by running python example.py, it kind of has this two-function call example, which then halts for 30 seconds, waiting for me to show you something. So let's talk a little bit about GDB basics. You can connect to a running process by running GDB and then the path to the program, and then any kind of arguments after that. So when you run a Python program, you're using user bin Python generally. When you type Python, that's the binary that you're using. And so you can launch your program with GDB. You can say GDB user bin Python, and then the first argument is the module that is the entry point for your application. So you can use GDB effectively to just start your application, at which point it's already connected to the CPython debugger, to the CPython interpreter. You can also, and I very rarely do that, the thing I do all the time is I connect to a running process by its PID. So GDB takes this -p option, and you specify the PID as its argument, and this lets you just kind of start your application the way you normally do, and as it's running, you can just say, oh, I want to see what it's doing right now. Let me connect to it with the -p option, and you specify the PID. As soon as you connect to it, GDB halts the execution, and this is the way that GDB works, and like most debuggers, it halts it, and so you can continue execution but just by hitting C for continue, and then you can stop it again later with Control C, and you just kind of see where you end up. You can then detach the GDB from the CPython interpreter using Control D, and that's disconnecting this link that you see back here. So you connect to it, and then you can actually detach, which will disconnect it, and your application just continues on as it did. So those are some basics. Let's have a little demo. How's the size? Is that good for everyone? All right. So what I'm going to do is, how about I get into the right directory? Okay, so this is that same application that I described and showed a minute ago, which is the example.py. It's the same code. So what I'm going to do is I'm going to run example.py, and it shows me its PID, which is 8506. It's waiting for 30 seconds. It's already in that sleep statement. I'm then going to use GDB and the -p option, and I'm going to give it the 8506 call here. And at this point, we've made the connection between GDB and the CPython interpreter. And what you can see on the screen here is a whole bunch of text output. And GDB has a lot of output. Again, like, I'm not an expert. I don't understand every little bit of it. But what you're looking at mostly here is GDB reading these debug libraries. So let's just take a minute and talk about compiled languages and debugging them with GDB. When you compile your language, you end up, or when you compile your application in something like C, you end up with a binary compiled version, right? And you can run that binary compiled version. What you'll also get with certain compilation options is a debug info package or asset, artifact, that also comes out of compilation at compilation time. And this debug info library is basically a map, that an artifact that can be used by GDB to connect to the binary that you just compiled and have important information about the compiled binary that you're inspecting. So for instance, you compile a function call, and that function has a name, right? The binary doesn't store that name. It doesn't care what that function's name is. It's a function, and it makes sure that every time it's called, it points to the same place, right? So if you're debugging it with just without the assistance of a debug info library to help support your debugging, you will have a very tough time getting any meaningful information. Because when you think about your C code, you think about it in terms of the source code itself, and there are these function names and there are variable names, but then if you don't use this debug info library and you just try to debug it just straight up with GDB without the debug info, then you're going to get, not nonsense, like you'll be able to see the values of variables, for instance, because the values are definitely there. And you can get some good information if you're really skilled at the art. You can have a good understanding of it, but you won't get these nice, pretty things that match up, like names, that match up with your source code originally. And so what you see here on the screen is it's reading these debug info libraries that I've installed. And so when Python is compiled for your distro or wherever you got your Python from, somewhere there are these debug info libraries available for you. So I'm running Fedora 24 here right now in a Vagrant VM, and Fedora, for instance, provides you Python, Python packages out of its normal repositories, and people are probably familiar with those. There are these other repositories that contain nothing but debug info libraries. And so they basically just put all of those over there, and what you'll need to do is to enable them, which is very simple. And when you enable the debug info library, for instance, in Fedora, you can then DNF install something.debuginfo, and you'll have the debug info libraries available on your system. GDB will automatically find them, and GDB knows the binary name, and it stores the binary name and the version, very strict version number, and you need an exact match of the debug info library, because any small change and that debug info might not be appropriate for it. So it kind of sounds a little complex, at least it did to me when I first started, but that's kind of the gist of it. So you can install these quite easily. I mean, no matter what distro you're on, debug info libraries are somewhere, and you can figure out how to install them. And once they're installed, GDB just discovers them, and it knows which ones it needs because that information is packed into the binary. And so when I'm debugging Python, which is, since we just connected to this example.py process, it knows, oh, I need to read libdl, I need to read libutil, libm, libc, ld-linux, libdyn, anyways, a lot of things. So at the bottom, you can see, well, a couple of things. There are these lines here, so they say thread debugging using libthreaddb enabled, so that means that it's threading aware, and a little further up, you can see, I I go up here? This is kind of the preamble for GDB here. And I'll show you the threading stuff later in the second example, which actually has a bunch of threads in it. So at the bottom, you can see GDB, this cursor, which is the GDB prompt here at the bottom, and this is how you get to interact with the source code. Now, I'm using screen here, so I'm just going to switch to the original place where I ran my code. Notice, it's halted. So, I mean, well more than 30 seconds has passed by, and yet it's just still waiting here, and that's because we've basically halted the interpreter, and it's just waiting for my input from GDB. So one of the first things you'll do in GDB is to look at the full backtrace. That's generally the first thing you want to do. Oh, wait. And you do this with the BT command here. So this is a backtrace as outputted, a C backtrace. This is frame 0 is at the top, and that is actually the deepest call. If you're using PDB or RPDB, the order of the stack frames is reversed. So with PDB and RPDB, the deepest call that you're into, the moment where you've halted execution deep down in your function calls, is at the bottom of the output. But here it's reversed in C land. And you can see at the top, frame 0 is a call into select. And select is a kernel facility that allows you to efficiently wait for a certain amount of time without kind of polling. And the kernel has efficient implementations to wake up when that select has completed. And so this traces the call all the way down to the kernel. And you can see that call there at frame 0. So this is a lot to look at, and so rather than try to explain all this right here, I've pulled out snippets of it, and I'll just highlight two kind of cool things that you can see from this output, and then we'll move on to some more practical usage of GDB. So this is a little snippet from that same output that you just saw, and this is a single function call in CPython. So these 3 frames, 8, 9, and 10, represent one Python call. And so inside of CPython, on its internal implementation, it has these frames that it thinks of. And a frame is basically a single step, a single depth of the normal Python call stack. So when you think about like making a function call, internally in CPython, it thinks of it as a frame. And that frame stores all the code associated with that and all the arguments that have come into it. And it calls fast function, which is part of the internal CPython implementation. And it calls call function, which is another C-based method inside of CPython. And then it calls this PyEval frame X, which actually does the evaluation. And you can already see some interesting things here. For instance, it says in frame 10, line 14, that point in the Python code is at line 14 of my example.py. And so this is some of the kind of raw information that you can get out of here, but as you'll see in a little bit, there are much better ways to do this, but I wanted to explain kind of the internals of this. And this is actually a really cool way to learn more about CPython if you're into that kind of thing. You can just use GDB to basically say, oh, what is Python doing when I do this? Or what is Python doing when I do that? What is CPython doing when I do this or do that? So like I had said, highlighted a little bit earlier, this is a call all the way into the kernel, and so it does not debug past that point. I mean, you can use GDB to debug the kernel, but that's a different topic altogether. And so frame 0 is usually going to be a function call into the kernel. I mean, it might be that you just happen to, catch it while it's just running in user space, at which point frame 0 would not be. But if you generally, well, not generally, but you have a pretty good chance that frame 0 is a call into the kernel. So that is a look at the upper end of the call stack there with BT. So, of course, at this point, I mean, like if I was sitting in the chair and the first time that I ever experienced these things, I ran BT on the application I was debugging, and I was like, oh my gosh, this looks crazy complicated. How is this ever going to be useful to me? And that's when I learned about these things called Python extensions for GDB. So thanks, David Malcolm, for contributing these to upstream Python. These landed a while ago, as in years. Even if you're on, for instance, an operating system that's been out for a long time, like RHEL 6, for instance, you have the version of Python that you're running has been compiled with these extensions. And it's these extensions and the debug info libraries that were produced at compilation time that work together to help make this debug experience practical, simple, and very useful. So thanks, David Malcolm. At the end of the slides, there's a link to the area of the ticket in Python's issue tracker and feature tracker, which talks about all the discussion and actually shows the commit that David Malcolm has made and others in terms of bringing this about. So if you're interested in more of the tooling about that's creating what you're going to see here, there's a link at the end of the slide. So here, these are some of the calls that these Python extensions for GDB provide us. And what these let us do, and we'll go through each of them kind of quickly, and then we're going to see some nice demos of them in action. But what each of these do is they let us not think so much about the C-based implementation, even though we're connecting with it, connecting to CPython and using GDB. It lets us instead just think about it as Python. So for instance, like if you're using PDB, for instance, and you show the call stack, you're going to see nice, clear Python code in that call stack, right? Well, guess what? If you use py-bt, for instance, you're going to see nice Python code. And so it takes those, for example, those 3 frames, those 3 C frames, the C call stack, and it collapses them into a single one, and it strips out all the information that's meaningful, and it literally shows you the original Python source from that. And so that's what py-bt does. PyList will show you the source. So that's like the list command in PDB, or L, as I typically use. And so that literally kind of shows you the original Python source, even though you're doing it through GDB. And that is quite a feat that has been put together. This is just such a great tool. PyLocals will show you all the locals from the current thread. So those are all the variables that are allocated in the current frame of Python. So in the Python, in the Python frame. And then PyUp and PyDown let you go up and down the call stack, and not the C call stack. It's letting you go up and down the Python call stack, even though you're doing it in GDB, which I think is still quite a magic trick. So we're going to look at these in action. So PyList, for instance. Let's go back to our little demo here. That is part of the debugging. It comes with the debug info libraries when you install them for Python. And if you're going to do kind of any meaningful debugging of Python, you're going to want to install at least the minimum set of those. And when you start GDB, it will tell you at the bottom, it'll say, I'm trying to find these debug info libraries because it knows the name and the version from the binary. And if it can't find them, it's going to say, I can't find these. And different distributions do it slightly differently, but all of them will tell you exactly which ones you need to install. And so it's very helpful to, it'll literally, on Fedora, for instance, it will literally say, here's the command you run to install it. So once you install those, you will have all of these tools. The ability for GDB to more meaningfully inspect the binary of CPython, and this extra tooling that kind of comes around it to better interpret those stacks.
What was the package name again?
The package name is, generally they're called debug info libraries.
No, that's the libraries, but I'm talking about for GDB to be able to execute the like.
Yeah, there's nothing additional.
Oh, it just comes with
It does. Yeah, but it comes with the debug info libraries because debug. Because that's part of the Python compilation. Does that make sense? Yeah, so for instance, GDB does not natively do it. So for instance, like if you, you'll see at David Malcolm's contribution to Python, he made 100% of the functionality that he did to create this was committed to Python. There was not a direct contribution to the GDB project itself. And so it's actually for that reason that I know that these tools that we'll see come with the debug info libraries. And you're receiving them because those debug info libraries were produced from a compilation of Python that came after and includes David Malcolm's work.
So when I install the Python debugger
Yes.
library, it includes this.
Yes,
Okay.
that is exactly correct. And just to unpack that a little bit, for instance, this is what I used. This single line will enable your debug info repository and install the correct debug info for you. And this command literally was shown to me from GDB. And so sometimes it has a hard time finding debug info libraries, and we'll come back to that at the end as kind of like a little gotcha. But even though it's kind of a stumbling point that I'll talk a little bit more about later, generally you connect to your application with GDB, you watch what it tells you at the bottom, you try to do it, you connect again, you do what it says again, and you just kind of iterate as far as you can go with that. And generally, you know, your mileage may vary, but it's always worked out for me, and I suspect that it will for you too. And also, yeah, if you have questions, I like that you asked that. If something is confusing, just feel free to shout it out. So you hit enter and you go through these C Python frames here, and you can see there are 19 of them. And the other kind of interesting thing here is that you can see how Python itself starts up. There's a lot of a preamble here in terms of how Python begins to execute. So you can use this technique to learn a lot about how Python works, which is way cool. But what I wanted to show you, right, was this. PyList. Good, I caught it before I left. Thank you. And so this is super useful because now you can take your running compiled version and you have no idea what it's doing. Like, what is this thing doing? I have no idea. And you can connect to it, and then if you have your original source available, you can use this. And PyList isn't really doing that much, right? It's looking at the C Python stack. It's looking at your source code. It's figuring out where the instruction pointers are, and it's showing you the instruction pointer, which is shown there at line 5 with the caret. And so you can also do some other things. Control L? Yes, thank you so much. That's an excellent suggestion. Thank you. Yep, so this is our PyList output. So let's just play around with some of these other commands. Here's a PyBT. And this is very much akin to what the call stack that you would see output from PDB or RPDB, for instance. And so you can see here that there are 3 Python frames, even though the call stack from the C Python output was like 19 frames long. This is just a nice simple 3. And so that's the power of these tools and how they can help you quickly get insight into what your application's doing. You can also, you can py up to take me, I'm going to go up a frame, and notice it says I'm going up to frame 7. That's in the C Python stack. Okay, I'm going to go up one more. Okay, now I'm up at frame 10. And remember, I had said that function call in Python is represented by 3 C frames. And so you can see by just going up one Python frame, you are going up 3 C frames. So I haven't defined any variables here. So PyLocals shows me nothing. But later we're going to see a better demo. Can everyone hear me okay? Okay, sorry. So later we're going to see an actual application, and the PyLocal output there is going to be very interesting. So then when I'm done, I can Control C, and hold on a second. I can continue with this. I can continue with the C command, and like at this point, it's just back running, and then I can Control C again, and I can stop it one more time. And so this is how you kind of start execution and then arbitrarily stop execution. Setting breakpoints is, of course, like something you want to do with any debugger, right? But it's hard this way. And the reason it's hard is because the CPython interpreter code is interpreting Python code. It's building frames. It's calling those frames and executing those frames, and it's doing all the memory management and all the stuff that it needs to do. And so the same code paths in CPython are being run over and over and over again as it interprets Python statements, right? And so setting a breakpoint is tricky because you have to set it in a way that you would have to set it, and I don't have a technique for this. You would have to set it in a way that says, oh, not only do I need to stop at the I would probably stop it at the pi eval x call in Python, but not only do you have to stop it, in the C code of CPython, not only do you have to stop it there, but you have to stop it, I want to stop it when this Python function is being called. And the only way you can know that is by the data arguments that are being evaluated, or maybe the variable states of the pi eval x call, right? And so all this is to say that what you won't see in this demo are nice breakpoints to set. And that's probably a growth area for the tool set, which is why I linked to it at the end, because you too can contribute to make this happen. So with that, I'm going to disconnect from this with Control D. I'm going to say, yes, I'm done, at which point it will detach. That program will continue running for its remaining whatever time is left after 30 seconds, and then you will see this exit. So you connect to it, you do some things, you detach, and it just continues running just like it always did. And that's one of the reasons why this is such a great tool to use to connect to kind of production systems, because it's safe. Assuming that you can halt your application, and that's an okay thing to do, then you can connect to it and then do your information gathering and then detach, and it just keeps on running. So that's way cool. So with that, so we saw the PyBT example output here. So threads, GDB has great support for thread evaluation and for working with threads. So you can get info threads to show you information about all the threads that are in your process. The example we look at next is going to have has a good amount of threads in it. The current thread is marked with the star. And GDB is currently working on exactly one thread. And so that way when you list the BT output and look at the, or the Pi BT output, either one, it's working on the current active thread, the one that GDB considers active, not the one that's active at that moment in time. And so you can switch between, you can list the threads with info threads, and you can switch between the threads with thread ID, and then you can list BT on that thread. Okay, let me switch to thread 3. Okay, let me list Pi BT over there, or Pi locals over there. Okay, now thread 2. So a lot of times when I write little scripts to send to people to basically gather all this data and send it back to me, for instance, you can use this thread apply all pattern, which is a normal GDB built-in thing. And that says, apply this command to all the threads. And so I'll say, thread apply all Pi BT, thread apply all Pi list. And that's a really quick way to just show me all the information that's relevant about Python in that simplified Python output for a particular process that you're debugging. So core dumps are become really handy with this technique, right? Because what you can do is you can say, user who's experiencing the problem, please take a core dump. And you can do this while it's running and it's safe to do, and it will just continue running, and that's fine. So it's basically a snapshot from when the core dump was taken. and you just grab the core by PID, by its process ID. And you say, and gcore is the utility to do it, so you just install gcore on the system. And you say gcore by the PID, and you'll get this file, which will probably be pretty big. Core dumps are not that small, and so, but they're really useful. And if you're really troubleshooting something, you just need it. And so you get them to upload it somewhere and send it to you. And at that point, you can, let me fix this up a little bit. At that point, you can connect to that core dump with GDB also. You just say GDB user bin Python, and then the core file that they sent you. And you will be able to analyze that in just the same way. Yes? Yes. Yes, it does. So the question was, does this functionality depend on your system matching the version and environment from where the core dump was created? And the answer is yes and no. It's yes, because the binary of the information in the core dump will name the the binaries that it's trying to debug, so like CPython, for instance, and its version. And if your environment is different from where the core dump was created, it will show you when you start GDB, it'll say, oh, I can't find the right debug info library. And then you'll say, okay, well, I'll just install it. But for instance, if it's from a different distribution, right, that's probably not going to work because they won't have debug info libraries available for you. Most frequently, I'm debugging on the same distribution that my user is, or I'll find a box that has it, and I'll even find the same major OS version number and even major minor OS version number. But there's this one issue that I've noticed where a user's environment won't be fully patched and up to date, and then what happens is say they'll be like just a small little bit behind in terms of their patch level, and then time passes and new versions of debug info libraries and new versions of Python compiled are pushed out into the repositories, and the old ones are not available anymore. And so there's this kind of like vintaging problem that I have run into multiple times. So that's the bad news. The good news is that even though GDB is going to tell you that it needs a lot of debug info libraries, the truth is if you can just get the Python one to work, that's probably all you ever need. So to show you just a little bit about what I mean, the application that we're going to debug here in a little bit, oh shoot, okay, hold on, Control L. Okay, so like I had shown before, this is the single command to install Python. This is the one that you want to get right. You want to find that old version, you want to compile it again yourself, you want to do whatever you can to get this thing right, okay? But GDB is still going to complain, and in fact, it won't fully complain to you about all the debug info libraries that it needs until it has this, right? Because it actually uses this to then discover more binaries that it needs to understand, because when you have other, for instance, you can have C modules that are written in C that are runtime linked against your Python code, right? So the Python interpreter itself is calling into another compiled library. And so until you install this debug info library and attach to your application, it doesn't know enough to know that, oh, I'm reaching this point where now I need these other debug info libraries. So my general advice is get this one right and don't worry about the rest. Unless you specifically have to debug down into one of those other calls. So it's kind of a yes and no. Your environment should try to match, but if it doesn't match perfectly or GDB still complains, just keep going. And if for some reason you can't get what you need out of it, then maybe come back and work on it. Yes?
So the other thing you might want to consider is that on the target system where you do core dump, you want to have your view limit set big enough so the core dump will actually shut all.
That's a great suggestion. So the suggestion is to the A very good one is raise the U limit up, make sure that the U limit is high enough so that when you generate the core dump on the target system, that the entire core dump will be generated. Core dumps are large and they use a good amount of resources while they're being created, and so you need your U limit high enough to have a valid core dump of which to evaluate. All right, so similarly for the application that I am going to show next, after I installed the main debug info for Python and I reconnected to my application, it told me I needed all of these. And you know, you really don't need all of these, but that's the way GDB works. It sees a binary interface and it wants to have the debug info libraries to use it. So I installed them. It still complains that some of them are missing. It's really not that big of a deal for me because I can get out of it what I need. So with that, so one quick little sidebar, consider using strace. If all you want to know is what is going on, I mean, is it even doing anything? You can use strace to show the calls that are occurring between user space and kernel space. And so, for instance, if you have a loop that is waiting every 30 seconds, say, kind of like my previous example, .py, you'll see that select call, and you can see from the arguments of it, you can look in the man pages for select, and you can see that the arguments will give you some useful information. Oh, the first argument is the number 30, and it's a call to select. Well, I know my application. Okay, I know that this thing is running in this loop, and I can very easily and quickly get some information about what it's doing. Or maybe it's opening a file, or maybe it's experiencing an error. So the strace is just a great, really simple tool that you can use on a running Python application. And you can use strace to analyze an already running one, and you can use strace to start your application also. So quick little strace demo. This is the simplest thing ever. So strace Python example. These are all kernel calls, calls from user space to kernel space. I'm not a deep kernel engineer or anything, so what I can show you is, oh, it's at the bottom. It says select. I know that's a call to have something wait with tv_sec equal to 30. And so this is the Python code calling into the kernel and saying, kernel, please wait for 30 seconds. And after 30 seconds, it will finish. So strace is a really simple way to get some information out. And that's really what this is about. It's about getting information about what the heck is going on so that you can find and fix the issue. So here's a better demo. Like I said, I worked on a project called Pulp. Pulp has several processes, and each of them have kind of specific uses and functions. And so I'm just going to give you a simple example of debugging Pulp with GDB. And this is just a more practical example to show you kind of something more meaningful. So what I'm going to do here is I'm going to so these are some Pulp processes, and don't worry too much about the details here, except to say that this is the application that I'm going to debug, and there are several processes that I want to that I could choose to select to. With GDB, you're going to connect to one of these processes, and when I run the application, I know which one that I want to connect to, and so the one that I want to connect to the process ID that I want in particular with this little grep command that I made is process 7741. Now, this process is running as the user Apache. I am user Vagrant. And so if you're trying to debug a different user's application, you need root access or special privileges to be able to do that. And so when I run GDB this time to connect to PID 7741, I'm going to use sudo, because otherwise I will get an error and I won't be able to connect to it. All right, so like I had said, Pulp is a software software management and composition application, and so you can install a pulp server, you can fetch packages with it, and you can compose those packages into different repositories and store old versions of repositories, and then host those to your environments. So consider going to check out Pulp, but the point is that I'm telling you all this for is that what I'm going to do here is run a sync from a remote RPM repository. And while I'm going to hit this off, we're going to see some output happen from the command line from Pulp, and then I'm going to switch to my other screen real quick while it's running. We're going to stop GDB and just see where we land. All right, so this is Pulp doing its thing over our struggling kind of network connection here. Okay, it's downloading things. Okay, let me connect to it. Boom. So at this point now, if I go back, right, this is just frozen because my application has stopped, just like example.py had stopped. And here, you can see something that I wanted to show earlier, but I really couldn't. This new LWP, this new LWP is, that's a lightweight process, which GDB thinks of as a thread. And that's effectively what a thread is in kernel land, is a lightweight process. And so you can see here that it has 4 threads. And if I do thread info, did I do this right? Oh, info threads. So here you can see that there are 5 threads, and each of them has a thread ID, and you can see the call that each of them is in, and that's pretty much the useful information here. So the star, which is thread 1, is the one that we're currently attached to with GDB, and so you can say, you know, thread 2, thread 3, and switch between them. So switching to thread 2, okay, switching to thread 3. And now, if you do PyList, you can see that this thing has stopped at a sleep statement. And so thread 3 is right here at this point in my code. And you can also use the PyBT to show you the Python output version of the call stack here for thread 3 specifically. And so between these two tools, you can get a great idea of, hey, how many threads do I have? What are they doing? What, at this moment in time, where are they? And you can also see PyLocals, which is a lot more meaningful now. Well, this particular thread doesn't have a lot of useful stuff in it, but you can see these variable names. So this variable interval is equal to 10. Oh, the name is PyMongo server monitor thread. Oh, that's useful. Thread 3 is a PyMongo monitor thread, part of PyMongo. It's a dependency. And so I can very clearly see, okay, thread 3, I know what that's doing. I can see the call stack. I can see the instructions. I can see the state and the variables and all the stuff. I can also go up, which takes me here. And I can go up again. I can go up one more time. So this is me just kind of like walking up the stack. And that's really the long and short of what you can do with this. So for instance here, so I've gone up the stack a little bit, and it shows you frame 15 in this kind of like dense output here. But because I walked up the stack some, if I use PyLocals here, you can see all of the variables that are allocated to this particular thread. So since I'm almost out of time here, I will talk about just one or two small things. We've kind of covered the gotchas, which you correctly identified early on, which is that you need debug info libraries installed, and you need them to be the same version as the one GDB wants. There's this optimized out option, so when you compile Python, it takes these different options, and sometimes you'll see in the GDB output, it'll say optimized out. Usually, that's not the part that I need, but you'll see it in there, and depending on how efficient your compilation is, you might see more or less of them. So it's just a gotcha, it's a thing to know. And then root is required to connect to other people's processes. So this is kind of the last substantive topic here, then we'll have just a minute for questions. do something proactive in your Python applications, right? And there's something very great that you can do, and it's this. You can put a RPDB set trace that is triggered with a signal. And now that I've shown you like all this complicated stuff that you might have to do, here's something you can do proactively. You can put this code into your Python code, and it will bring in RPDB into every time that it runs, and then you can trigger it with a signal. And at that point, you can send a signal to your application, and it will stop at that moment and open up the network interface. This for you to connect to it with Telnet. This does not resolve if you can't connect to that thing, and so this is not a cure-all for all situations, but consider building this into your application. This is part of RPDB, the normal RPDB feature set. So it's something you can do to help your future self. Yes?
Depending on where your server is located in the network, it might not be a good idea to use 0.0.0 for that. You might want to use localhost instead, so that it's only access shell access on the host.
That's a great point. So the point was that this example would listen on all interfaces, and that might not be a good idea. And so consider using localhost instead. That's a wonderful suggestion. I will likely be updating my slides. Yes, sir. So the observation was that this call will remove your ability to strace the process. And you're probably right about that. And I think that what you're driving at is that you're now using a different signal. You're overriding the use of the signal. Yep. Yep. So this technique might reduce or completely eliminate your ability to use strace if you're using this technique. You could probably attach it to a different signal or write your own signal handler so that they stay out of each other's way a little bit better. Yes, that's exactly right. And actually, Celery itself supports this functionality, just as an example of user 1 and user 2 as signals that are free and available for use to trigger this kind of debugging, network debugging. So these are the references, and these are the slides. We are pretty much at the end of the time. Are there any last questions? Yes? The question was, have I ever used this technique to debug async I/O? Or what was that next part? Or greenlets. No, I have not done those things. But anything that is interpreted with CPython or any compiled interpreter, this should be successful for. You may need more debug info libraries, but this should work with greenlets and debugging async I/O code as well. Yes? Yes? Yep. So the bug that I found was was in a dependency, not our code, but in a dependency, and it was an error condition that would occur very rarely, which would trigger a syntax error because that line was almost never interpreted and it had a small error in it, which would cause a thread to die without any enunciation that it died, which would bring the other threads to a halt. Yes? I did not. The question was, on some Linux systems, you might need to enable PR control, and I didn't quite follow the rest of it. The set ptracer flag. Oh yeah, the set ptracer flag. I have never had to do that. All right, thank you all so much, and thanks for the great organizers here at SCaLE. We're out of time.
Test, test. Test, test. Okay, why don't we go ahead and get started? Okay, how many have stopped by the Arden booth in the exhibit hall already? So most everybody. So this is a birds of a feather session. So this is more of a discussion. We do have some slides in PowerPoint that we could go through, but I'd rather not do that. I'd rather have more interaction and cover any questions or detail that you didn't get from the Arden booth to go over. I'll kind of play it by ear. If there's no questions, then we'll start doing a few PowerPoint slides